morning, everyone. Today we're gonna discuss loss in machine learning. On your handouts, you'll see all the points covered here. If you don't have a handout, you can also scan the QR code and it will take you the same handouts electronic copy. I plan to make this interactive, so I encourage you to ask questions and we'll have some discussion points throughout the handout as you can see. So they're not in the right order, but as and when you guys come up with a question, I think most of them should fit in the sequence that we see there. Okay? Start off. Let's say you wanted to predict the house price. Imagine you have to train a machine learning model that predicts house prices, let's say in Madison. How do you know if the predicted prices are closer to real prices? In this diagram here, let's say that was the actual price, which is more, but the model predicted the price to be lesser than that. So we see that there is a difference in the actual price and the predicted price. And loss lets us understand how far is our prediction from the truth. So loss is a key measure in machine learning that lets us evaluate how well or poorly a model is performing. Just going a bit for making a formal definition out of that. A loss function is a metric. For example, in this example, we saw that the actual price and the predicted price were different. So a loss can be a metric that quantifies the difference between the predicted value and the actual value. Loss also tells us how bad our model's predictions are. For example, in this example, the loss could be as simple as just the difference, the subtraction of the actual price and the predicted price. At this point, I want to take a pause and point us all to discussion point 1. So it says, can you think of examples where, so in general, you might have gotten a feeling that we want to minimize loss. Like we minimizing loss means that the model is getting better. The difference between actual and predicted is getting smaller and smaller. So can you think of examples where just decreasing the loss, just optimizing, minimizing the loss may not be a good idea?
Maybe if you have like student grades,
Yeah.
so you don't want everybody to get an A, or maybe, what the model predicts, it depends on how the student is, so it's always expected to be some kind of natural variation.
Yeah. I think that's a valid answer. That's a valid answer, and it's also an important one. It highlights that not always do we have to focus on minimizing the loss. In general, at a high level, it feels like minimizing the loss would be a good thing, but sometimes we want things like explainability or fairness. We don't want the model to learn the bias in the training data. But that was a good answer. Thank you. So, going ahead, what are the types of loss function? Depending on the type of problem, for example, in regression tasks where we have to predict a continuous value, the loss function that we use is called mean squared error. So it's the difference between the y, which is the real value, versus y hat, which is a predicted value. We take a square of that and we sum them all up and divide by the number of examples. Similarly, for classification problems, where we have to predict a class of the objects, so for example here it's a 3-class classification. It's only showing a portion of the network, but we're trying to predict whether the image was a horse, zebra, or a dog. So in that case, we have to predict a class, and the loss function used is called cross entropy. In case of, can you guess how many classes would it be for binary cross entropy? Two? Yeah, that's right. So for 2 classes, this is the loss function that we have. Yi is the ground truth class and yi hat is the predicted class. And at this point, I want to take a pause and ask if you guys think there could be a different loss function, let's say in the regression problem. Can anybody think of any loss function different other than this one?
You could remove the squared, so just the minus.
Just the absolute difference of that. Or we could also take something called as average, mean average, things like that. So all of those are used in different scenarios, but they all can be used. Okay, going forward, so we have different losses for different problems. And in general, we might have seen that we are trying to minimize the loss. So here it shows that we have high loss, the robot is not happy, medium loss, it gets happier. And as the loss keeps on going low, the model gets better, and the robot, which is the AI model, gets trained more and more. So the goal of training any ML model is to minimize the loss. Smaller loss always means a better prediction, and the model is closer to the real ground truth. But we also saw that it's not always the thing that we want to maximize for. What you see there in the example, does anybody know what that is? Has anybody seen that?
It's trying to find a valid solution for our problem.
Yeah, it's trying to find the valid and the global optimum solution. So it's trying to find not just a local minima, but a global minima. And the thing that we see there is a loss curve landscape. So does anybody know how do we do that? What's the optimization algorithm called? Just a guess?
I think you mentioned it. Is it cross entropy?
Not quite. Not quite. That's a type of loss function. But once we have a loss function, how do we minimize that? Okay, I'll give a hint that it's like rolling a ball downhill.
Ice ball.
Yeah, it's like letting a ball slide downhill. Like any guess? It can be wrong. It's okay.
Ball slide.
No, but that was pretty close. That thing is called as gradient descent. Gradient descent, yeah. So
Is that the only way you can minimize loss?
I think there must be more, but just in general, optimization problem, convex optimization problem, just to find the minimum of that. That's the algorithm that's followed. But except in ML problems, it's much more difficult because the landscape is not so easy. It has millions of parameters, so there will be many local minima, not necessarily like global minima. So key takeaways, we saw loss measures, how well the model is performing. We also saw that the goal is to minimize the loss to improve model predictions. And loss functions need to be chosen as per the type of problem. Now I want to take your attention to the last discussion point, which is that imagine we had a self-driving car. What do you think could go wrong if we trained the model on certain data set and we had very small loss, so we thought that the model is doing well? But do you think it will always do well in real world settings?
I don't think so.
Yeah, for example, what do you think could go wrong?
What if the behavior in the data set already wrong?
That could be a thing, but usually we spend a lot of time cleaning up the data set, so a lot of effort goes into quality of the data set. But that is true. Trash in, trash out. So if the model is trained on poor data, the model will make wrong predictions. But on the same, in the same type of example, you could also think of, for example, if the self-driving car was trained on a data set of only daytime images. So will it work at night? I don't think so. I mean, it may work, it may not work. It will definitely suffer. So we have to make sure that if we want to drive the car at night, the data set needs to have a training data for daytime. Similarly, if we are training it in cloudy images, winter images, sunny images, and we are testing it in something that it hasn't seen, it will suffer. Also comes down to signs on the road, just the road conditions, how many trees are around, is it like a indoor setting or is it more of outside, things like that. So that's something that we need to pay attention to. Just minimizing the loss on one certain thing doesn't always mean that it will perform well once it's deployed. That was all, and do you guys have any more questions? I think James hasn't asked any questions yet.
Um, like, how long have you need to spend when you want to train in a
Yeah.
specific model?
Yeah, I think that's a good question, James. Thanks for that. So it brings up a question of how do we know when to stop the model training? And how do you know that it has been trained enough? And there is a small caveat though. So for example, if we keep training a model too much, something called as overfitting will happen, where what it means is that the model will learn and memorize the data, training data too much, but it actually hasn't learned anything, it has just memorized it. So there is a sweet spot. There are ways to check for overfitting, and if we see that the model has overfitted, what we can do is add some more loss terms that will penalize the model for getting too close predictions to the ground truth, and also having a separate test set and training set, so that if we train the model on something, we must test the model on something that it has never seen before. That's the only way that we'll know that the model will perform well in the real world settings as well.
Okay.
Does that answer your question?
Yes.
And I was wondering, so in what scenarios do you actually want to minimize loss completely?
In most of them, it's just that, for example, in cases where you minimizing the loss, but usually if you make the model more complex, it will minimize the loss. But let's say it's a loan bank application, like who gets a loan and at what interest rate. In that case, let's say you train a model that's really complex but not interpretable, and when customers come in and you tell them that your loan has been denied, you can't explain why, because it's like a black box model. So in that case, a model that has more loss, that is less complex but more interpretable, more explainable, versus a model that's that has better, it minimizes the loss more, but it's not interpretable. So it's a trade-off like that. But in general, we always want to minimize the loss. Does that answer your question?
Yes, it does. Yes.
Okay. Thank you. That's all I had, guys.
Yes. Nice.